Let us continue our discussion on the derivation of the gravitational field equations. So, towards the gravitational field equations, since we have already discussed this in previous lecture, let us number it 2. So we have just let us just recall that Maxwell's equation govern how the electric and magnetic fields respond to charges and currents, right? So Maxwell's equation, they tell us how the electric and magnetic fields respond to charges and currents. Similarly, the gravitational field equations, which we will soon see, are called the Einstein's equations. They should govern how the metric responds to energy and momentum, which is what matter has. Ultimately, the field equations has to be postulated and tested against experiment. First of all, let us recall that when you actually proved or when you actually talk about Newton's law, you have never proved Newton's law. It was postulated, and people have seen from performing experiments that the law is correct. So we will motivate basically in two different ways. First, we will be motivating by some informal reasoning, closely what Einstein himself was thinking, and secondly, by starting from an action and then deriving the corresponding equation of motion. So the informal argument begins with the realization that we would like to find an equation which supersedes Poiseuille's equation, right? Because that's what the equation in Newtonian gravity is. So the equation is nothing but grad square of the gravitational potential equal to 4 pi g rho, where you can think of this grad square to be same as delta ij del I del j. It is basically the Laplacian in space, and rho is the mass density. Now we will ask the following question: what characteristics should our sought after equation possess? So let us look at this Poiseuille's equation carefully. On the left hand side, we have a second order differential operator, which is the Laplacian, which is acting on the gravitational potential, and on the right hand side we have the measure of the mass distribution. So when we try to generalize this in case of relativity, we require a relativistic equation which generalizing the Poiseuille's equation grad square phi equal to 4 pi g rho. A relativistic equation generalizing this should take the form of an equation between tensors, because that is the first and foremost criteria. We are now looking into general coordinate invariance. Therefore, each and every quantity that will be there in the equations must need to be tensors. Now we know that the tensorial generalization of mass density is the energy momentum tensor. So we can easily say that the right hand side should actually be replaced by energy momentum tensor, which we already have discussed and denoted by TAB. The gravitational potential, which is there in the left hand side of the Poiseuille's equation, should get replaced by the metric tensor, because that's what we also have seen, that phi should be replaced by GAB, because we have seen this many times that we had to relate a perturbation of the metric to the Newtonian potential to basically successfully reproduce gravity, which we just saw previously in the previous lecture, and also earlier we had convinced ourselves why this Newtonian potential should be the metric. So we might guess the equation of the form which will represent relativistic gravity to be of the form grad square GAB, or better I should write it like this. This grad square G, this is kind of a tensorial equation that we should, in fact I should not even write the equality sign here. We should be writing something proportional to TAB. In fact, this is the first guess. Whether it works or not, that we have to still figure out. So here comes the second order derivative of the metric. Now, although the left hand side of this equation, which we have just guessed, the left hand side of this equation is not a sensible tensor, it's just a suggestion or suggestive notation rather, to indicate that we would like a symmetric 0 2 tensor here. So symmetric 0 2 tensor should be here, which is second order in the derivative of the metric. In the derivative of the metric. Why symmetric? Because the right hand side we have a symmetric tensor. Therefore, we already know that the energy momentum tensor must be a symmetric tensor. Therefore, the left hand side should also carry something which is symmetric. Of course, what should be the first choice in this case? The first choice or the first guess should of course be the D'Alembertian in curved spacetime, which in principle can be written as this covariant derivative, and then this acting on GAB naturally leads to 0, because this is automatically 0 from the metric compatibility condition. You remember metric compatibility criteria? Metric compatibility criteria said that del A GBC equal to 0. So as soon as we have something like this, and then acting this operator on GAB would make this thing to be equal to 0. So our first guess did not work. Fortunately, there is an obvious quantity which is not 0. There is an obvious quantity which is non-zero and which is constructed out of second derivative of the metric. As well as the first derivative of the metric also is involved, and this is nothing but the Riemann tensor, curvature tensor. You just recall that in a shorthand notation, R contained derivative of the Christoffel symbol and the product of the Christoffel symbols, and this Christoffel symbols in turn were containing the derivative of the metric. Therefore, this term, the first term here, should actually contain the second derivative of the metric. But it does not have actually the right number of indices, does it? Because this has this R, A, B, C, D. It has 4 indices here. So the thing that we were discussing in the previous page, where we required only 2 indices to be present in the left hand side, because right hand side we were more or less certain that it should be represented by the energy momentum tensor if there is something which is equivalent to the mass density on the right hand side of the Poisson equation. Therefore, this choice of Riemann to be placed at the left hand side of the proposed equation is also not correct because of extra indices on Riemann tensor. We needed 2, but we got 4. So Riemann tensor is ruled out. Although we can construct a second rank tensor by contracting the first and third indices of the curvature tensor, which in principle is called the Ricci tensor. Therefore, it is tempting to actually write RAB equal to some kappa TAB. Remember, in the equation which we wrote in the previous page, there was a proportionality sign. So this kappa is introduced, which tells you that this kappa is a proportionality constant. In fact, Einstein did suggest this form of his field equation, where this RAB equal to kappa TAB, with RAB being the Ricci tensor. At one point of time, Einstein also did suggest this one. There is a problem, unfortunately, with the conservation of energy. If we actually want to preserve this structure del A TAB equal to 0, we then must require del A RAB to be equal to 0. This is certainly not true in an arbitrary geometry. Any arbitrary background, it cannot be guaranteed that the covariant derivative of the Ricci tensor vanishes. In fact, we had seen while deriving the Einstein tensor from the Bianchi identity this thing. If you remember, go back to our old calculation, and if you remember, we had somewhere this kind of form while we derived the Bianchi identity, which is equal to 0. Therefore, this immediately implies that del I RIL is equal to half of del L R, or I can also write it as del I r lower IL as half del L r, but we already proposed is of the form RAB equal to kappa TAB. Therefore, this immediately implies if I multiply both sides by G upper AB, this is equal to kappa G upper AB TAB, and this therefore implies R, which is the Ricci scalar, is equal to kappa times T. GAB times RAB is nothing but the Ricci scalar, and GAB times TAB is nothing but the trace. So taking this together, we require, taking everything together, we require del A T to be equal to 0. If at all we require del A R to be equal to 0. But the partial derivative is same as covariant derivative for a scalar. So this is a scalar. So t, and t is a constant throughout space time. This is highly improbable since t equal to 0 in vacuum while t is not equal to 0 in matter. So it is almost impossible to satisfy this criteria. Okay. So we have to try harder. This equation also does not make sense. So we have tried to, it's kind of a trial and error method. This does not work. The choice of the D'Alembert operator did not work. This type of equation with RAB equal to kappa TAB, it also didn't work. And now we already know one tensor which has all the above mentioned properties. Or above required properties, and this we have just discussed, and that is called the Einstein tensor. Remember, we discussed this when we discussed the Bianchi identities. So that Einstein tensor, just to remind you, had the form RAB minus half R times GAB, which this tensor GAB always obeys del A GAB equal to 0. We are therefore led to propose that GAB equal to kappa times TAB should be my form of the field equation. So in more expanded form, this should actually look like RAB minus half R times GAB equal to kappa times TAB. This of course requires highlight. So this is a proposal that we actually can make for the form of the field equations. So this equation satisfies all the requirements. For example, the right hand side is a covariant expression of the energy and momentum density in the form of a symmetric second rank covariant tensor. And secondly, the left hand side is also a covariant form in the structure of a symmetric 0 2 tensor. Why I can say that this right hand side as a whole is a symmetric tensor? Because we have already proved that RAB is a symmetric tensor. RAB here is symmetric in A and B, and we already know that the metric is symmetric tensor, covariant second rank tensor, and R here is a scalar. This R is of course the Ricci scalar, so it is a scalar, it does not matter. So overall the left hand side also is a symmetric second rank tensor. So this is constructed from the metric and its first and second derivative. Now the task that remains is to fix kappa. We have to fix this proportionality constant which we had introduced at the very beginning, and to see whether the result actually reproduces a Newtonian gravity as we know it, or in other words, does this equation predict the Poisson's equation for gravitational potential in the Newtonian limit. So we would like to see if this form of the Einstein's equation predicts Newtonian gravity in the weak field time independent slowly moving particles limit. So for that, let us actually consider something called perfect fluid, the energy momentum tensor for which is given by rho plus p UA UB plus P times GAB, where these UAs are the force velocity of the fluid, rho and P are the rest frame energy and momentum densities. In fact, for Newtonian limit, we may neglect the pressure. Roughly speaking, the pressure of a body becomes important when its constituents move with speed which is close to the speed of light. So we in principle can consider P to be equal to 0. Consider P to be equal to 0, and therefore the energy momentum tensor is of the form rho times UA UB. We now choose that we are in the rest frame of the fluid, that means we are sitting on the fluid. So this is also a choice. We choose UA to have only the time component, the spatial components are not changing. Then we know T00 is nothing but rho, and T alpha alpha are all 0, where alpha beta, all the Greek indices represent spatial coordinates or spatial indices. And what was the trace? T, which is nothing but TAA, which is equal to rho times UA U lower a, which is equal to minus rho. because we already know UA is -1, which is time-like. Now we need to find out the Ricci tensor in the Newtonian limit, and for that we first note that we are considering the metric perturbation of this form GAB is equal to eta AB plus HAB. Remember what we are doing? Again, let us remind ourselves, we have proposed this form of Einstein equation. Our task is to fix this k, the proportionality constant. The only way to do that is first by considering the limit which is already known to us, which is the Newtonian limit. That means we should be considering the weak gravitational field time independent slowly moving particles limit, and we try to figure out if we can get back the Newtonian gravity, namely the Poisson's equation, from this proposed form. And for that we have actually figured out that we should actually work with this perfect fluid for which the energy momentum tensor is given by this form. And then for the weak field limit, we have assumed that the metric can be expanded around the Minkowski or flat space time with a small perturbation given by HAB. So in order to find the inverse of GAB, in fact in the previous lecture I had actually written the covariant form of GAB from this expression with a minus sign here in between eta AB and HAB, but I did not prove it. So I have to figure out what this GAB is in terms of this eta AB and HAB. So for that we start from this expression GAB GBC, which is equal to delta CA. So if I now take the variation of this object GAB GBC, this is Kronecker delta on the right hand side, therefore this is equal to 0, and we have delta GBC G lower AB equal to minus G upper BC delta G lower AB, or we multiply both sides by G upper AD, okay, and then minus GBC G upper AD delta GAB. So we have already derived this expression many times. So this is nothing but delta G, B is replaced by AB AD. Okay, so let us actually write it down like this: delta G CD equal to minus GAD GBC delta GAB, because this is going to give me another Kronecker delta BD, and delta BD here B will be replaced by D and we will have this thing. Now then let us actually think that, let us write this G upper AB as G bar of some upper AB plus delta G upper AB, where G bar upper AB is nothing but eta AB. It is the background metric around which one is perturbing around, and delta GAB is equal to our HAB. Okay, suppose that the inverted metric is of this form, where explicitly G bar AB should be the flat space time metric and delta GAB should be our HAB with covariant indices. Then this equation actually gives us delta GCD equal to minus GAD GBC delta GAB, which is equal to minus eta upper AD plus delta G upper AD times eta upper BC plus delta G upper BC times HAB. Okay, we have actually now put back this G upper AD as eta upper AD plus delta GAD, which is nothing but HAD, and G upper BC as eta BC plus delta GBC, but this delta GBC in our mind we know that this is nothing but H upper BC, and delta GAB is nothing but H lower AB. But now if I multiply term by term, this actually gives us minus eta AD, eta BC, and then BC, then HAB. We all neglect the higher order terms in H square, or neglecting order H square terms. You know that this delta GAD is of the order of H, this is of the order of H, and overall there is a multiplication by H. Therefore, all the terms like eta BC times delta GAD times HAB will be neglected. Terms like eta AD delta GBC times HAB will be neglected, and so on and so forth. What will remain is this eta AD, eta BC, HAB, but this is really nothing but minus HCD. So this immediately gives us G upper AB is nothing but eta AB minus HAB. So this is a very important result which I had proved in the previous, I did not prove in the previous lecture, but then someone actually asked that how this is minus sign. The minus sign comes because of this. So in fact there is another nice way to check. So let me just briefly mention this, that there is another way of checking why there should be a minus sign. So suppose I have been given this GAB, which is nothing but eta AB plus HAB, and of course I know that the inverse will also be a linear combination of, so inverse of GAB, that is G upper AB, will be a linear combination of eta upper AB and H upper AB. This already I know, it cannot be anything else. So what we do is that, okay, let me divide this into two parts. So let us choose G upper AB to be equal to, say, A bar eta upper AB plus B bar H upper AB. And then what we have is this GAB, GBC is equal to eta AB plus HAB, and G upper BC is nothing but A bar eta BC plus B bar HBC, and then this, the left hand side we already know it's a Kronecker delta, delta AC, which is equal to now you see that this is eta AB and eta BC, so A bar delta AC plus A bar plus B bar HAC. So these terms are coming because there is a product of eta AB with HBC, and eta AB with HBC is nothing but HCA, and there is a product, there is a multiplication of B bar with that term, and then there will be a term like HAB with A bar, with A bar eta bc, and hab with a bar eta bc will also raise one index here and we'll give it to the same thing hac, and then there will be terms like hab and hbc which we have already neglected, and this therefore is nothing but delta ac. Okay, so it is only possible that this is true, it is only possible to be true if a bar is equal to 1 and b bar equal to -1. Then this term, the second term goes to 0 and this equality holds. So the upshot of this discussion is that if you are given a GAB with covariant indices as eta AB plus HAB, you want to figure out what is the contravariant GAB is, there is a overall minus sign in, no, sorry, not overall minus sign, there is a minus sign in between eta AB and HAB, that you should be remembering. Now, since the spatial components of TAB are 0, remember we started with energy momentum tensor and we had just seen that the spatial components of such an energy momentum tensor that we had chosen is 0. So the proposed field equation, let us remind ourselves, the proposed field equations that we had written was RAB minus half RGAB, which is equal to kappa TAB. What we want to do now is that we actually multiply this with G upper BC, RAB minus half RG upper BC and GAB, which is equal to kappa G upper BC TAB, and this gives us R BB contracted, so RCA minus half R, this will give us delta CA is equal to kappa T CA. So this can therefore be written as R minus half R into 4, which is equal to kappa T. If we make C equal to A, then this is the equation that we will get. Okay, so this will immediately imply R to be equal to minus kappa T. So therefore, when we write RAB minus half RGAB equal to kappa TAB, we can also write the equation in this manner. Let RAB be there plus half, we replace this R by minus KT, so therefore there is a plus sign which is equal to kappa TAB, and this implies RAB equal to kappa TAB minus half GAB into T. This is also another form of Einstein equation. Of the Einstein equation. Now we have already figured out that the TT component of the energy momentum tensor is rho, the trace of the energy momentum tensor is minus rho, and all the spatial components are 0. Therefore, I can write the equation which we just derived, RAB equal to kappa TAB minus half GAB into T, to be like this, that R00 equal to kappa into T00 minus half G00 into T, which is nothing but kappa T00 is rho and then minus half T is again minus rho, so it becomes a plus, and g00 is nothing but eta 00 plus h00. So this equation overall remains kappa rho plus half kappa rho eta 00 plus h00. Now we know that eta 00 is equal to -1 and h00 as a whole is much less than eta 00. That was one of the conditions. Therefore, keeping the conditions of this perturbation in mind, this becomes kappa rho minus half rho, which is nothing but half kappa rho. We now need to find R00 again from the definition. So recall that R00 is nothing but R A0 because by definition, when the first and third indices of the Riemann-Christoffel curvature tensor is contracted, that gives us the Ricci tensor. So the Ricci tensor therefore can be written as, so I know the form of this Riemann when A is contracted, so I would like to write it explicitly. This is del A with respect to this index A gamma A00 plus del 0, there will be a minus sign, del 0 gamma A0 plus, it should be gamma AB gamma B00 minus gamma A0 dummy B, and then this would be gamma B A0. So this is the form of the Riemann or the Ricci, whatever you want to tell. So let us look at what we have now by looking at this expression of RA0A0. So this second term del 0 gamma A0, this contains the time derivative and it vanishes for the static field. So this immediately is equal to 0 because gamma A0 will contain the derivative of the metric. But we have said that we will be considering the time independent cases. Therefore, this term will be 0 by definition. Now, this on the other hand, these two terms are the product of two gammas, but gammas are first order in metric perturbations, and hence gamma square type of terms, which these terms are, these are actually gamma square of form. So these gamma square contribute only at second order, and hence this can be neglected. So when you explicitly write, let me repeat once again why this can be these two terms can be neglected. When you write down a single gamma in terms of these GABs, remember that GAB is written in terms of eta AB and HAB, where HAB was very small. Now, when you write this down in terms of the eta AB and HAB, the derivative of eta AB anyway is 0 because eta ABs are all constants, and then there will be terms like derivative of the HABs. But this derivative of the HABs are actually multiplied twice, one from this, another from this. So these are all higher order in Hs. Therefore, all such terms which are product of gammas should also be very small, and therefore they should be neglected. So what we have is RA0A0 is equal to R00, which is nothing but del A gamma A00 after neglecting all these terms. This becomes derivative with respect to A half, let us write the explicit form of this gamma A00, GAM minus del M G00 plus del 0 g m0 plus del 0 g 0 m. So this is the form of the gamma. Now again you look at these two terms here. These are the time derivative of the metric. Therefore these are all 0, because again let us remind ourselves that we are considering only the static cases where the metric is not changing with respect to time. Therefore these two terms are all 0. So what we really have is this del A half, okay, g upper am, and then minus del m g00. That's it. So let us write it like minus del a half. Let us also break this g upper am with eta upper am minus h upper am times del m h00. Again let us remind ourselves that this g00 is nothing but eta 00 plus h00, and when derivative acts on this eta 00, it anyway is 0, because eta 00 is minus 1, which is a constant. So this therefore becomes minus half del a of eta am del m h00. This is simply because we will have to neglect the terms like ham times del m h00, because those are higher order term in h. So this will therefore become minus half eta ak eta am del a del m h00, which clearly is minus half del m del lower m h00, which is minus half Laplacian of h00. But remember, we also have proved that earlier that this is somewhere here. We have proved this half k rho. Where did we prove it? Here. So this was r00, which is nothing but half k rho. Here also we have obtained r00. This is nothing but r00, and we have obtained r00 in terms of the metric perturbation h00. Therefore what we really have, by comparing this with this, we can write half k rho equal to minus half Laplacian h00. This immediately implies Laplacian h00 equal to minus kappa rho. Now we already have seen in the previous class that h00 is nothing but minus 2 phi, where phi is the gravitational potential. Therefore this equation immediately tells us minus 2 Laplacian of phi equal to minus kappa rho, and therefore Laplacian of phi should be kappa by 2 times rho. So this is precisely Poisson's equation, exactly same as the Poisson's equation, provided we choose kappa to be equal to 8 pi g. So this is exactly Poisson's equation, provided we choose kappa to be 8 pi g. Therefore, everything in mind, we have the form of the Einstein equation to be RAB minus half R GAB equal to 8 pi G TAB. So this is the first time we had written, after fixing all the constant and everything, the form of the Einstein equation. This tells us how the curvature of space-time reacts in the presence of energy momentum, where this capital G, of course, is Newton's universal gravitational constant. It has nothing to do with the trace of GAB. So please keep in mind that this capital G here has nothing to do with the Einstein tensor, the trace of the Einstein tensor GAB. Now the other form, therefore, there is another form which we had introduced throughout this lecture of the Einstein equation. The other form of that equation should now look like 8 pi G TAB minus half trace of the energy momentum tensor time GAB. This is also another form which is frequently used. So the difference between these two forms, this form and this form, is purely cosmetic. In substance, they are both the same. And when we say that we have to write vacuum Einstein's equation, that means your TAB is 0 and what you have is just RAB equal to 0. In vacuum, TAB is 0, therefore you can write directly using this equation that RAB equal to 0 is the form of the Einstein equation in case there is no matter. And this is true like when you want to figure out the geometry outside a star or a planet is determined by this equation. Or any massive object, so as to say. When the planet is somewhere else, the outside this matter distribution of the planet, outside geometry is always given by the equation which is RAB equal to 0, which is vacuum Einstein's equation. Okay, so let us stop here because the next thing in the next class what we will do is basically try to figure out the same set of equations from an action principle. We had roughly given ideas of the form of the Einstein equations. Yesterday's class also we had a lot of discussions about this, and today's class we gave some heuristic concept. And the next class, the next thing that we need to do is that we need to figure out the same equation by using a variational principle.